Hi there, Mr. Sutton here with the BC Calculus 7-1 Extra Practice Solutions on derivatives and integrals of series. For this problem, we're given this g of x function, and we want the first four non-zero terms and general term for f of x. All right, so the big relationship between g of x and f of x, you might notice here, is that f of x is actually the derivative of g of x. So in order to write a power series for f, it would help if we first had a power series for g. G, as it happens, is a geometric kind of setup because we have this 1 over 1 minus r format. So our geometric setup here, a1 value is going to be 1, and then r is going to be whatever you're subtracting from the 1 in the denominator, so that's going to be negative x squared. So just we'll write out the first 5 terms of that series just in case there's any constants that are going to get differentiated away. So we've got 1. And then we just keep multiplying by negative x squared. So we're going to have minus x squared plus x to the 4th minus x to the 6th. And we'll do one more, plus x to the 8th. And now for the general term, we're going to have a negative 1 to the n power times x to the 2n. Let's go ahead now and take the derivative of this series. And that will actually end up giving us f because, as we said before, f is the derivative of g. So going left to right and differentiating, this 1, as we predicted, gets differentiated away. It's just 0. So our first term we're actually writing, our first non-zero term, is negative 2x plus 4x cubed minus 6x to the 5th plus 8x to the 7th. And those are our first 4 non-zero terms. Now for the general term. The negative 1 to the n is just a constant, so it hangs out in front. But we have our power rule that we can use here because n is really a constant. So this is going to be 2n x to the 2n minus 1. On this problem, given the g function, we want the first 4 non-zero terms and general term for this f function down here. Now the key on this one is realizing that f is really the derivative of g if you use the either the quotient rule or if you just bring 1 minus 2x up with a negative 1 exponent and take the derivative, you'll end up getting this down here. So we're going to first figure out a series for g of x, and then we'll take the derivative of that, and that will end up giving us the series for f of x. So g, turns out, is geometric. We have an a1 value, a top value of 4, and we've got an r value, whatever's being subtracted from 1, of 2x. So writing out that series, and I'll do five terms just because we're about to take the derivative, so we'll probably lose one of those. So our first term is 4, and then multiplying by 2x each time, we've got 8x plus 16x squared plus 32x to the 3rd plus 64x to the 4th. And now for the general term, so we're going to have an x to the n, we're going to have a 2 to the n, and then out in front of all of it, we need a 4 for that first term. So I'm going to write 4 times 2 to the n, x to the n. All right, let's go ahead now and take the derivative of this because, as we said earlier, f is really just g prime. So going left to right, this 4 is gone, but we have an 8 for the first non-zero term. And then we follow that up with a 32x, just using our power rule here, 96x squared, 256x to the 3rd, and I'm glad I don't have to do any more because I probably would have lost track. But over here now for the general term, this 4 stays out in front, as does the 2 to the n. These are all constants. The only thing we have to differentiate is this x to the n. This is just going to use the power rule because n rather is a constant here. So this is going to be n x to the n minus 1 with all that other stuff out in front. For this problem, we're given this g of x function that's 1 over 1 minus x, and then they turn around and tell us, hey, this series here is a power series for f of x. Based off of that, they want us to find a function for f of x. So the key on this one is realizing that they're giving you this g of x for a reason. We've got a regular function, we've got some other functions series. There must be some connection between these. So let's take the g function and create a series out of it, compare it to this series, and see if we can recognize what the relationship is. So g is in general a geometric sum form. We've got a1 over 1 minus r format here. So because this is a geometric essentially, I'm going to write out a geometric series. I have a starting value of 1 and an r value of x. So just writing that out, we've got 1 plus, and now we just multiply by x each time. We've got plus x squared, plus x cubed, and so on and so forth. So what's the connection between g and f in series form? Well, if you look at these terms term for term, it looks like to get from g to x, you would have to take, it looks like, the antiderivative. So we've got the antiderivative of 1 would be x, the antiderivative of x would be 1/2 x squared, and that pattern does keep going. So that means that f is the integral of the g function, specifically the integral from 0 to x. Because you'll notice there's no term out in front of this x. X is the starting term, so everything else must have gotten zeroed out. So that means that to find the f as a function in regular function form, we just need to take the antiderivative of the g function here, which is just going to be, let's see here, this would be ln 1 minus x, but we have an inner tail of -1, so negative ln absolute value 1 minus x, that's going to be our f function. On this problem, we're given this g of x function, and we want the first 4 non-zero terms in general term for f of x equals ln absolute value of 1 plus 3x. So why are they giving us these two different functions? Well, if you look closely, you'll notice that this f of x function here is actually the integral, the antiderivative of the g function, right? If you take the antiderivative here, you're going to have 3 times ln of all this stuff divided by a tail of 3, so that 3 gets canceled out, and you've just got ln of 1 plus 3x. Well, given that this is the antiderivative of this, we just need to figure out the series for g of x, and then just take the antiderivative of that series, the integral of that series actually, and that'll give us this f of x function. Okay, so let's get our g of x series. This is geometric. We've got a1 over 1 minus r format here. So my first term then is this numerator of 3, and then r is whatever I'm subtracting from 1, so in this case that would be negative 3x. So writing out my series, I've got 3, and then multiplying by my r value, we've got negative 9x plus 27x squared minus 81x cubed, and I just need 4 non-zero terms for the f function here, and this is going to give me that when I take the antiderivative, so I just need my general term now, which is going to be, let's see, we're going to have a -1 to the end, so we can alternate. We also are starting with a 3 out in front of everything, and I'm also going to have to multiply by 3 to the n and x to the n. So all of this stuff. Now, I guess instead of having a 3 out in front and then having another 3 to the n, you could just do 3 to the n plus 1, and that would also work. All right, so let's take the antiderivative now of this function, term for term. Now, just thinking ahead a little bit, when I take the antiderivative, and I'm going to do this from, we'll say, 0 to x here, because I've got all x's here. There's no, like, x minus 2 or anything. When I take this antiderivative, it's going to end up zeroing out all my terms when I plug in 0 on the back end. So when I do my antiderivative from 0 to x of this stuff, I don't actually need my evaluation box with the t's in it, because again, when I plug 0 in, it's just going to zero everything out. So I'm just going to go straight to the antiderivative in terms of x. So that's going to be 3x minus, and this will be 9 over 2x squared. Then we've got 3 for the exponent, so that's going to be 9x to the third. Over here, this becomes a 4 for the exponent, so minus 81 over 4, x to the fourth. And now for the general term, the constants all just kind of kick around and stay there. But we have n plus 1 now for the new exponent, so we're going to divide by that. So out in front, I've just got -1 to the n, 3 to the n plus 1, all of that divided by n plus 1, and then we've got x to the n plus 1. On this problem, given this f of x function down here, we want the first 4 non-zero terms in general term for the integral from -1 to x of f of t dt. So in order to take the integral of this thing and get actually terms of a series out of it, I'm first going to want to write out the first 4 non-zero terms in general term for this series here. So my first term is going to be whatever I get when I do 0 for my n. That's essentially raising everything to the 0, so that's just 1 for that first term. And then after that, we're just going to be multiplying by negative x plus 1 each time. This is essentially a geometric series. So we've got negative x plus 1 plus x plus 1 squared minus x plus 1 cubed. And that's enough to give us our first 4 terms of our integral. So let's just go to the general term, which is just this summand in sigma notation. Okay, next we're going to take the integral of all this. And since we're doing the integral from -1 to x, when we anti-differentiate all these, we're going to get still a bunch of parentheses with x plus 1s in them. So when we plug in this -1, that's going to end up zeroing out a bunch of stuff, but it's not going to zero out the x we're going to get when we take the antiderivative of 1 in the very beginning. So we're actually going to have to use the evaluation box for this one, and that means we're going to have to express things in terms of t when we take our antiderivative inside the evaluation box. All right, so our first thing then, we're going to have a t instead of 1. T is the antiderivative of 1 when t is the variable of integration. Minus, this is going to be 1/2 t plus 1 squared. And we would divide by the inner tail, only it's a derivative of 1 in here, so we don't really have to worry about that chain rule too much. Next, we've got 1/3 t plus 1 cubed. And then finally, minus 1/4 t plus 1 to the 4th. For the general term, this -1 to the n is just staying out in front. That's a constant. But we have an exponent of n plus 1 that we're going to divide by, and we'll have a t plus 1 to the n plus 1 for the actual variable term. And this is all being evaluated from -1 to x. So we've got all of this stuff with x plugged in, and then we're just going to subtract all of this stuff with -1 plugged in. Now when I plug -1 in, again, it's going to zero out everything that has a t plus 1 for a term. The only thing that doesn't get zeroed out is the t in the very beginning. So I've really just got -1 that I'm subtracting from all of this. But if I'm subtracting -1, I'm actually adding +1. So I'm just going to put a little +1 out in front of this whole thing and call it a day. On this problem, they're telling us this geometric series here represents the function f. They want a function that represents the integral from 0 to x of f of t dt. So it would first be helpful if we had a function to actually represent f instead of this series. So I'm going to put this series in function form. Since this is a geometric series, the function is just the sum of this infinite series. So we use our infinite sum formula for a geometric series. A1 in this case, that's our first value we would get if we plugged 0 in for n. That would just be 1. And then r is whatever I keep multiplying by over and over. So that's this x minus 1 piece here. So then I have 1/1 minus x minus 1, which would probably be helpful to simplify. So this ends up being, let's see, 1/, this is going to be a +1, so 2 minus x. And now I need to take the antiderivative of this thing from 0 to x. So when I'm doing this, just looking at my answer choices, I notice that I've got x minus 2 in all of the expressions instead of 2 minus x. So I'm actually going to take a -1 out of this thing, and I'm going to take the integral, the negative integral, of 1/t minus 2 rather than 2 minus t, just so I can get this expression to match what I already have in all these answer choices. All right, so antiderivative of this is actually pretty straightforward now that I've got a positive t value in here. This is just going to be negative ln absolute value of t minus 2 evaluated from 0 to x. So this is going to be, let's see, a negative out in front, and inside we've got ln of x minus 2 in absolute value minus ln of -2. Well, ln of -2 in the absolute value is just ln of +2. And if I'm subtracting these logarithms, then I can actually merge these together in a fraction. So I can call this negative ln of, and then it's just one thing divided by the other thing. So x minus 2 over 2. We've got that negative out in front still. And looking at my answer choices, this is going to be answer choice D.